Yeah, that's it. Okay. All right, so I think we're recording now. All right, so our first section, and we're going to focus a lot on this all year long. Isometric transformations. Now, I know you guys at some point in little kid school done transformations. Anybody remember anything about transformations? What? Feel what? Okay, so maybe you did translations and reflections, rotations, dilations maybe? Okay, so that's what we're going to do that. We're going to go a little deeper than you did before. But has anyone ever heard the term isometric? You know what it means? You've heard it, you don't know what it means. Okay, someone just said it and you said, I don't know what you're talking about. Can I please still stand here? So another word for isometric is rigid. Iso meaning equal or same, and metric meaning movement, right? Or measurement. Okay, so they don't change size or shape if they're isometric. Like if I take this pen and translate it over to here, has it changed in size or shape? If I rotate it, has it changed in size or shape? That's isometric or rigid. Okay. So most of our translations are, and you probably are familiar. We look at some of these examples here with the terms pre-image and image. Okay, so if we start out with something, we have a pre-image. I think I want to do a slightly different color here, actually. Yeah, that one stands out. We start out with a pre-image, we do something to it, and what do we end up with? The image. And you notice this is, well, it's a pentagon, right? 5 sides. It's not a regular one, right? Labeled B, C, D, E, F. Do you see the difference in the image after we do something to it? What are those called? You know, little marks. Prime marks, right? So this point C would correspond over here to C prime, right? Et cetera. D to D prime after you get done, okay? And it looks like it was rotated, yes? Okay, so that's pre-image to image. Oh, yeah, definitely rotated because they said so, okay? And so the next one is a translation. They just slid it over, and these points here, I, J, H, correspond to their primes over on the other side. And then a reflection is just like looking in a mirror, right? You end up with you have like a reflection line, right? And flip it over that line. I don't know what that sound was. Okay. All right, so those would be some isometric transformations, or rigid, right? The terms are generally interchangeable. Before we go to the next section here, I want to give you a quick note. So I'll just make a note here, and you will. See notes. Number 1. Okay, and a couple pages out here, you'll see I have a blank page for notes. Is that, yeah, can you see? All right, if that happens, just I can't see. Notice it's not right there, okay? So note number 1 here, if everybody flip to this page where it says Notes Workspace, from time to time we'll take advantage of this because the stuff in this book doesn't always address things ahead of time where I want them to, okay? So we have a little thing called scale factor. Okay? So if we're making something bigger or smaller, we do so by a scale factor, okay? Which we generally represent, this thing, here's why we work by the letter K, right? By the letter K. And that is, if we're making something bigger or smaller, K is just a multiple of enlargement or reduction, okay? It's the multiple of enlargement or reduction. Has anybody ever, kids don't do this so much these days, put together like a model car, boat, or something like that? And what? Yeah, okay, so on the box, it probably has a scale factor, like 1/16 or something like that, right? Which means it's not an enlargement of the real car, it's a what? Reduction, smaller, right? 1/16 the size, isn't it? So that's just the scale factor. So, like for example, and by the way, if there's notes that you miss here or whatever, in addition to the video, I also paste the PDF of the notes on the team site. Okay, so especially if you miss something, I'm in your way. Don't sweat it. It'll be on my website for the team site. Okay. So, for example, how did I do that? See, I've forgotten completely how to write. Okay. If K, our scale factor, equals 5, what do you think that means? The image of our pre-image is what? 5 times larger, yeah. So it's 5 times larger. Okay? If, on the other hand, K is, say, 1/3, what do you think that is? So phrase it correctly. It's not 1/3 smaller, it's 1/3 the size, right? If you think about that for a minute, you'll see what I'm getting at, right? So it would be 1/3 the size of the pre-image. Okay? All right, so that would be an enlargement, something like 1/3 or 0.5 would be a reduction, wouldn't it? Okay? Okay, we got that. Let's go back to where we were. Now, these three up here are isometric, or rigid, okay? So now we're going to talk about one that, or two of them that are not isometric. They're not rigid. So we actually end up changing size this way, giving the scale factor, okay? So we have a thing called a dilation. A dilation just means to get larger or smaller, right? Anyone ever seen anyone that's currently on, like, on drugs? How do you know? What? What about their eyes? Their pupils are dilated, right? Okay, they're dilated. That means they're, what, larger? Yeah, larger. Okay, good. What do you know? All right. So I'll be checking you when you come in. Okay? Since you seem to know someone. So example 1, dilation. It just gets larger in both. Like, so if it was on the XY coordinate plane, right, it gets larger in the X, maybe like 5 times, and equally 5 times larger in the Y, right? X and Y, okay? So equally in both dimensions, okay? Now this would be a stretch, okay? So it's not really dilation, okay? What's the difference between, say, this stretch and a dilation? Yeah, it only got larger in one dimension, didn't it? It didn't get any larger in the Y dimension, correct? Okay. And again, in example 3, that's also a stretch. So a stretch here is where one dimension scale factor is different than the other dimension scale factor, okay? And with a dilation, both dimensions in the X and the Y, both their scale factors are the same, okay? So that would be a non-isometric, okay? Remember, isometric, we stay the same size. This would be non-isometric. Can anybody, let me ask you though, so dilation is not isometric, right? Generally, can anybody think of a dilation that would be isometric? Like what scale factor would cause a dilation to be isometric? Maybe it's kind of weird and obvious. What about that? Scale factor of 1. 1 to 1, right? You're thinking, well, of course, then it's not really a dilation. Well, maybe kind of technically it is a dilation with a scale factor of 1. And hey, Mr. Alo, it seems ridiculously obvious, maybe, right? But that would make the dilation isometric or rigid, right? And even though it's ridiculously obviously, thinking about that might help us later down the road when we run into some other things, okay? So now we have, I remember I told you this class is really rigorous. Some of these sections early on make it look super friendly. They get puppies and all that, right? Okay. What's that? Yeah, I think it's a pit bull. Okay. So I want you to circle which of the following are isometric transformations. They've given you this pre-image here, okay? And of these three, which of them is isometric? A, B, or C? Why did somebody say it? I don't wait for hands raised, like, I don't look back and see who raised their hand, just, shout it out. If it gets crazy, then I'll start asking for hands, but which one of those is isometric? Yeah, right? Which one do you think that is? The dog, it's the dog, yeah, it's the dog, that's right. It's the rotation is what I was getting at, okay. All right. So here, now you might have to flip back and look, okay? So they want us to circle for that first image A and B and C, which of those it was. So in image A, if you have to flip back, which of these was it? Reflection, translation, rotation, dilation, stretch, or other?
Dilation.
Yeah, everybody agree that would be a dilation? Got smaller, if I remember, right? Now, how about the image in B? Stretch. We only got larger in one dimension. And then in C, I believe we already said it, right? It's a rotation. Okay? All right. Let's look at number 3 here. Let you guys work on that. Why don't you take number 3 and 4, all of you guys on your own? Circle the one, maybe there's more than one of you. That's the bill. And then answer number 4 for A, B, and C. In a second. What do we think for 3? Those are isometric.
A and B.
Good, A and B. All right. A and B. Go. A and B. And then number 4, which one is A? What's the bills? Yep, rotation. And B? It looks like a reflection. And C? I agree, stretch. All right, let's take a look then at the coordinate plane, but I want to give you a quick second note though. So before we get to this part, see note number 2. This page here. See note number 2. So I just want to talk real quick about mapping notation, which we'll make use of this year. Notation when we're in the coordinate plane. So when we're doing these transformations, another word for it, especially in the coordinate plane, is mapping the image somewhere, the image somewhere else. Yeah, notation. Okay. All right, so every point in the coordinate plane is made up of an x comma y. You all know that, right? Yeah, I've seen that before. Okay. And so say we wanted to translate some particular point or a group of points, some distance to the right, some distance up and down, right? So we could make a rule, right, that says the following. Any point x comma y in that 3 image, okay? And then we draw a little arrow. I'm going to write above the arrow. It's not part of the notation. It just explains what the arrow means, okay? So this arrow generally means maps to. Maps to. Okay? And you might see something like this for the rule. X plus 3, comma, y minus 2. Right? So let's say you had a triangle with 3 points in the coordinate plane, and every one of those points x, y, you apply this rule to it, and what do you think it does to the triangle? Okay, tell me which way. What would this do? So that x is this axis, right? Plus 3, the positive is to the right. And then, yeah, okay. So this would be a translation. Right 3 and down 2. All right? Be careful, don't just say over. Like over 3. Why? If it was x minus 3, like, oh, what do you mean by over? Which way, right? Okay? And then up and down for the y part of it. Okay? So for example, if I took this rule and applied it to the point 4, comma 1, what would be the new coordinates of that point 4, comma 1? 7, comma, come on, what's 1 minus 2? 1 minus 2 is negative 1. Okay. Right? And so the shape will have points, right? And you'll apply that rule to all the points, and the whole shape will get shifted that way. Say it's for a dilation, okay? I guess I was going to ask that later. Let's do a rule for a dilation, where every point xy maps to the following. Let's see, 2x, comma 2y. You see what we did there? That 2 is the scale factor k, isn't it? Kx, comma ky, whatever. So if it's 5 times larger, or 2 times larger in this case, whatever these points are would get twice as big in the x direction and what? Twice as big in the y, okay? So this would be a dilation not M. Hold on, it's been a long time since I've written. Dilation with K equals 2. Okay? And this would be an enlargement or a reduction. Enlargement. Okay? So for example, let's take our point 4, 1. And we apply this dilation rule to it, what would our new coordinates be? 8, comma 2. And you would do that to every point in, say, for example, the triangle. And they would all be dilated by the same, okay? So that's a dilation. What do you guys think, like, how would you be able to recognize a stretch? Yeah. Right, so maybe it would be 2x, comma y. Looks like the y is not getting the same scale, or 2x, comma 4y. Would that be a dilation? No, it wouldn't, because it's not equal in both dimensions, right? That would just be a stretch, okay? You get the idea? All right, let's go back to this here. So we have a pre-image, okay? And then they give us a coordinate rule. So here are this triangle ABC, and they've given us the coordinates of A, B, and C, and here's the coordinate rule. Every point, x, y, in that triangle maps to x, comma, negative y. Well, let's just take this rule and get the coordinates of the image after that. So where would A prime be? What would be the coordinates of A prime by this rule? Yeah, the x doesn't change, right? So it would still be negative 1, comma what? Negative 1. Good. How about B prime? 0, negative 4. And C prime? 4, negative 1. Good. Okay. Would this be an isometry? An isometry is just something that's isometric. It would be, wouldn't it? Okay? Even though one of these got multiplied by negative 1, it still doesn't change the size, right? Remember I talked about scale factor 1? So it keeps it the same size, okay? So it is an isometry. Anybody go? So it's going to be a translation, rotation, reflection. Any idea what those three would be? You think? It might be. Let's plot it and see. So let's plot these points. Everyone do that now. So negative 1, right? Huh? 0 and 1, 2, 4, and then 1, 2, 3, 4, 1. And then always label your transformation with the primes, okay? So this is A prime, and that's B prime, and C prime. So does that look like it was a reflection then of the original? What was the line of reflection then? Yeah. So we call this a reflection. In the x-axis. Okay? Whenever you say something's being reflected, you also have to state the line of reflection. Okay? We'll just say reflects. Well, some of the questions, like simpleton questions, but generally, don't just say reflection without saying in what line. Okay? What line is the mirror? All right, let's take a look at number 6. So I want you guys to work this one out on your own. Take a minute, okay? And see if we got the points for the pre-image. There's our mapping rule or coordinate rule, okay? Get those points, plot it, and see how we do.
0, -2.
0. 0, 0, isn't it? Okay. It's all right, it happens. That's 2 times 0, 0. How about B prime? 1, -6, okay? And then what? C prime? 5. Well, negative, yeah, 0 has is neither positive nor negative, right? It has that quality, so we just say 5, 0. All right? So when we plot them, hopefully your plot looks like this. I've noticed when you guys come in here, sometimes your plotting is a little, one thing. You get the X's and Y's mixed up or something, I don't know. I think this one goes off the grid a little bit. 1 down here, no big deal. 1, 2, 3, 4, 5, that. And this was A prime, and then B prime and C prime. Okay? So, was this an isometry? No? Why not? Yeah, so what would it be? Okay, but it's also something else though. Is it also, it's a reflection as well, right? So they combined it here, didn't they? See that? With that negative value of the scale factor, it flipped one of the coordinates over, okay? So I would say, yeah, it's a reflection in what line? In the x-axis. And it's a stretch. It's both. Okay? Both things. Okay, so that is that one. Let's so we have isometric transformations. Name me 3. And one more. Translation, right? Name me 2 non-isometric. Right, Dan? Dilation. Now, I will say after this, we won't be dealing with structures so much. From here on out, mostly it'll be dilations, okay? But the stretches are one of them. So for the problem set, right now, I'm going to have you all do it right now. And this will count as you get it done. You turn it. We're going to do just numbers 2, 3, and 5, okay? So for the problem set, just do numbers 2, 3, and 5. Okay, that should pare our time down a little bit. So I'll give you a few minutes here. I don't know, just see how long it takes you. Shouldn't take too long. Remember, do it in pencil.